Okay, so hi all. Thanks everyone who has made it all the way through to the very last lecture, still showing up in person. It is appreciated. Um, okay, so yeah, very last lecture of the course, except for next week, we'll have you guys giving presentations, answering a few questions, and so on. So the videos, of course, for your projects are due tonight at midnight. They should go in the Google Drive folder that Nam created. Next Monday, by next Monday, you need to submit questions for everyone else's videos. Yeah, and then in the lectures on Tuesday and Thursday, we're going to take turns to people will spend 2-3 minutes very briefly going over the topic to remind people, and then I'm going to ask a selection of the questions that you've submitted. Okay. So yeah, there'll be more about that on the Piazza over the next week. But for now, let's have one more lecture of me trying to teach you some stuff. So last time we talked about alternative models of quantum computing. In particular, talked about adiabatic quantum computers, measurement-based quantum computing. So that's sort of the end of our actually implementing quantum computers section of the course. We had the guest lectures on their areas of expertise, and then I talked about some wackier and wilder stuff. But today, just for the final lecture, we're going to talk about a pretty new topic. It's a one-off, small little thing, but quite a cool thing that I think needs to be covered in a quantum information course, and that is entanglement. Of course, we've talked about entanglement almost throughout the course, but today we're going to talk about it a bit more systematically and really try to understand it in the sort of modern, best quantum information theoretic way. Okay, so sort of so far in the course, we've sort of had this working definition of entanglement that works at least for pure states, which is that a state psi is entangled. State psi on two systems, A and B, is entangled if and only if psi is not equal to some psi A tensored with psi B. Okay. So if a state can't be written as what's called a product state, the state on system A and a state on system A, B, then we say that it's entangled. Of course, that's very much a yes/no definition, and you might say, what if it's really close to a state that looks like that? That's the product state plus some tiny epsilon correction. We'd like to say that sure, that's entangled, but it isn't very entangled. So we'd like to sort of quantify entanglement. And we saw that there was a natural way to do that, at least for pure states, which was this thing called the entanglement entropy. So the way the entanglement entropy worked is that look at the reduced density matrices C's, rho A and rho B, of this entangled state, psi AB. And then those reduced density matrices are noisy for entangled states. So they have an entropy. and they have in fact the same entropy, which we call the entanglement entropy. And we can, it's a perfectly reasonable definition to say that this quantifies the sort of amount of entanglement. Okay, so say we have one state that has a much larger entanglement entropy than another state. We'd say the first state is more entangled than the second state. That's sort of a reasonable definition. We're gonna give another definition today that for what it means for one state to be more entangled than the other, that will slightly disagree with that definition. So we'll get a bit more sophisticated about even this setup for pure states. But what we haven't really talked about at all is, let's say we have some mixed state, so some bipartite mixed state rho AB. And then we just haven't talked at all about what it means for that mixed state to be entangled. So, you might think, well, it's just exactly the same definition as before. And certainly it's true that we can define a notion of a sort of product density matrix, product state, mixed state, just if the reduced density matrix, rho AB, can be written as a tensor product of a density matrix rho A with a density matrix rho B. And this is just like for pure states, this is equivalent to there sort of being no correlation between the state on A and the state on B. Okay, so the expectation value of a product of observable on A and observable on B will be just the product of the expectation values, for example. We have no correlation there. Okay, so you might say, great, so the answer is just like before, an entangled state, mixed state is just a state that can't be written as a product state. That might be a bit quick. So what about the following? Consider a state, rho AB, that is equal to half times just the 0, 0 state. So A being in state 0 and B being state 0, plus a half times them both being in state 1. Okay. So it's easy to see that this is not a product state. In particular, if you measure that the system A is in state 0, you always measure that the system B is also in state 0. Okay, similarly, if you measure system A is in state 1, you'll always measure that system B is in state 1. But if you just measure one of them, it's random whether it's 0 or 1. That's we have correlation between system A and B. But on the other hand, it is a sort of classical mixture of product states. Right, so if we interpret this state as a sort of ensemble, then it can be written as a sort of ensemble where there's a 50% chance that it's in the 0, 0 state and a 50% chance that it's in the 1, 1 state. Neither of those states are entangled. So we'd like to say that this state is also not entangled, right? It's just a probabilistic mixture of unentangled states. That if that's possible, if you can make entanglement just by having probabilistic mixture of unentangled things, then we could create entanglement at classical level all the time, right? This isn't going to violate Bell's inequalities or anything like that. So we'd say that this state has correlation, but it's only classical correlation. It's not quantum entanglement. Okay. So that discussion very naturally leads to sort of a definition. And that definition is of something called a separable state. Okay, so a separable state, density matrix, rho AB, is by definition a probabilistic mixture of product states. Okay, so for example, this state up here where the PIs would both be a half, and the rho AI and rho BIs would be 0, 0, and 1, 1 respectively. For I equals 0, they'd be 0, 0, both be 0, 0. I equals 1, they both be 1, 1. Okay. So we can define an entangled state. So sort of classically, any classical probability distribution over sort of classical states, classical mechanics, everything would be separable, right? That would be all it was. Everything, all correlation would come from probability distributions over states where just system A is in state 1 A and system B is in state B. So we therefore define pretty naturally entangled states just as non-separable states. Okay. Any questions about that definition and why that definition makes sense as a way to characterize when a density matrix is entangled or not entangled?
I have a question. So if you had some generic density matrix on A and B, and you did like a Schmidt decomposition between A and B, treating them as like vectors, then presumably.
So how are you doing a Schmidt decomposition? So for a pure state, I can do a Schmidt decomposition. Are you doing?
I'm just saying, like, treat the density matrices as vectors in like some larger Hilbert space.
Oh, okay. Yep.
And you do a Schmidt. Presumably, the reason why this wouldn't work to always write a state like this is because they wouldn't be density matrices.
Yeah. Good. So, wait. How are you wanting to do this? So if you're treating the density matrices as pure states, you have like 2 copies of A and you have 2 copies of B, right? And then you're trying to Schmidt decomposition into the 2 copies of A and the 2 copies of B.
Mm-hmm.
So that's just a different thing you're going to get there, right? So wait, let me think about this. Yeah, good. I think yeah, the answer is that they won't be density matrices. Yeah, they'll just be completely arbitrary matrices, and
okay, thank you.
Any other questions? Okay, awesome. Okay, so that's that's a basic definition. But we want to do more. Again, we wanna define a notion of states being more entangled or less entangled or barely entangled. So let's try to think about how we can do that. Okay. Well, okay, the first thing we might think is well, last time with pure states we sort of did that using entanglement entropy. Can we do the same thing here? But it should be pretty clear immediately that sort of the entanglement entropy no longer works the same way. So in particular, if we look at the reduced states, rho A and rho B, then the entropy of rho A is in general not equal to the entropy of rho B. And of course, both can be non-zero, can be arbitrarily large. not just even for separable states, but even for product states, right? If my state is rho A tends to rho B, then rho A and rho B individually can be anything you want. So just by looking at them, we can't quantify the entanglement at all. So we're going to need to be a bit more sophisticated, and sort of the attitude that's developed over the last few decades in quantum information is that the right way to define something like entanglement is to define it in terms of what you can do with it. That's the sort of motivated way to quantify things like this. So that's what we're going to try and do. Going to try and define entanglement operationally. Okay. So this will hopefully become clearer in a minute what I'm going to mean by this. But the basic idea is that we first define some set of things that we're going to call non-entangling operations. Okay. So what things might we count as a non-entangling operation? Anyone want to throw out an idea for something you could do to a quantum state that sort of can't create entanglement, or we don't want to think of as increasing entanglement?
Could you swap two qubits of the same system?
Yeah. So do some say A consisted of 2 qubits, then you could like swap them. That's totally example. It's actually more general than that, right? Like sort of any unitary circuit that we apply that acts only within A shouldn't be able to create any entanglement, right? Because it's completely disconnected from B. So one of the things we're going to allow as part of our non-entangling operations is just going to be sort of local unitaries acting just on A or B. Okay. So that's one of the things we're going to allow and count as a non-entangling operation. What other ones won't we have? Well, there's other stuff that sort of Alice or Bob could do on their own in their own labs that manipulate their system, and that we'd want to say can't create entanglement because it's just Alice or Bob doing something on their own. And that's that Alice or Bob could do a measurement, right? They could measure their system in some way. So we're going to allow local measurements on A or B. Okay, so these two things are collectively called local operations. It's just being done in Alice and Bob's lab separately. Okay, but there's one final thing we're going to allow Alice and Bob to do that we don't think should be enough to let them create entanglement. And that's we're going to allow them communicate, but we're only going to allow them to communicate classically. We're going to allow them phone each other up and like tell each other things. So allow them classical communication. And really the sort of useful classical communication, we firstly decide in advance together what local operations they're each going to do, is obviously important. But the real important thing, the thing that you need classical communication in the middle of the process for is Alice can tell Bob sort of her measurement outcomes. Right, so they might know in advance what measurements each other are going to do, but then they actually do those measurements, and they need to be able to phone each other up to tell them what measurement outcomes they got. Okay, in particular, being able to do that means that Bob's sort of later operations on his system can depend on the early measurement outcomes. Okay. So these three things are collectively known as LOCC, local operations classical communication. Okay. Any questions about how they're defined? Why this might be a sensible thing to define as non-entangling operations? Okay. Hopefully, it should be pretty intuitive that just using these three things. Yeah. So if I start with a separable state, row B, should be reasonably obvious that just using these classical communication from Alice to Bob and local unitaries that depend on that classical communication, depend on the local measurements, then I can get from my starting separable state to any other separable state right. So all separable states are equivalent to one another, can be interconverted between each other just using these local operations and classical communications. But also, I can't get to any non-separable state, so I can't create entanglement. And the reason for this is just, let's look at what these three things can do. If I have some local separable state and then I apply a unitary to A or to B, that's just going to leave me with another separable state. If I do some measurement on A and B, then yeah, again, in each of the, it's just a mixture of product states, and each of the product states doing a measurement will leave me still with a product state. So I'll still have a mixture. And classical communication, you can signal the measurement outcomes and can create correlation between the two sides by doing, say, a random measurement, then signaling that measurement outcome, then doing something different depending on the measurement outcome. But I can never create anything that's not a separable state. Okay. So that sort of motivates why this is a good definition of non-entangling operations. And we can now just make the following definition. Some state rho 1, bipartite system AB, is more entangled than rho 2 if I can get from row 1 to row 2 using just local operations and classical communication. Okay, so we're going to write that. We can represent row 1 with a dot and row 2 with a dot. And we're going to say there's a little arrow going from row 1 to row 2 if I can get from one to the other using LOCC. Of course, there is also the possibility that I can get both from row 1 to row 2 using local operations and classical communication, and also get back from row 2 to row 1 using the same set of operations, right? In that case, we'd say that they're sort of equally entangled. And we'd write this by sort of having, we have row 1 and we have row 2. and we have an arrow going this direction, and we have an arrow going back the other direction. Ooh. Okay, so this gives us a natural way to compare the entanglement of different density matrices, row 1 and row 2. But there's a very important point, which is that we can have states row 1 and row 2 where we can't go either direction by local operations and classical communication. Okay, we can't start with row 1 and get to row 2, but we also can't start with row 2 and get to row 1. So in this case, we sort of have these two dots, row 1 and row 2, and there's just no arrows between them at all. Okay, so in this case, we're just going to say that row 1 and row 2 are just sort of differently entangled, right? Like, if we had arrows going both directions, if we could interchange between the two, then they're sort of equally entangled. In this case, they're not equally entangled. They're distinct, you know, but it's not as simple as one is more entangled than the other. They just have different entanglement structures. That which one is more entangled depends on what you want to do with it, right? Like it might be that row 2 is more entangled than row 3, row 1 is more entangled than row 4, but neither, row 1 isn't more entangled than row 3, row 2 isn't more entangled than row 4. They're just different types of entanglement. Okay. So mathematically, the sort of structure we have that we get from this definition is something called a pre-order. So depending on how many maths classes you've taken, this may or may not be familiar to you, but it basically just means a relation between any two elements of a set. In this case, the set is the set of all states that needs to satisfy the following properties. Okay, the first thing is that it needs to be reflexive. Okay, what this means is that for any row 1, we have an arrow going from row 1 to itself, right? Using local operations and classical communication, we can get from row 1 to the same state, row 1. Okay, that's trivial, right? We don't have to do anything at all. So that's obviously true. And the second property that it needs to satisfy is that it needs to be transitive. Okay, so what this means is that if we have row 1, row 2, and row 3, and we can get from row 1 to row 2 using local operations and classical communication, and we can get from row 2 to row 3 using LOCC, then that implies that we can get from row 1 to row 3 using LOCC. Okay. On the other hand, we're not going to require, or it's not in general true, that this relationship is anti-symmetric. Right, so if it was anti-symmetric, it would be what's called a partial order. So that would mean that if there's an arrow from row 1 to row 2, and row 1 is not equal to row 2, then there's no arrow going the other direction. Okay, in this case, that isn't true, right? We can have two different states that are equally entangled, where you can go backwards and forwards between them with LOCC, and that's fine. And it's also not necessarily complete. Right, so complete would mean that every pair has an arrow going at least one direction between them, and we don't have that. We can have states that are just different entanglement structures that can't be compared by this ordering relation. Okay. Any questions on how we're defining entanglement, like what this pre-order is, anything like that?
Can you repeat once more what anti-symmetric means?
Anti-symmetric means having an arrow from row 1 to row 2 implies no arrow from row 2 to row 1.
I see.
Okay.
Thank you.
So that would make this what's called a partial order, which means, you know, it's really like one thing is always either bigger than another, or they just can't be compared. In this case, we also have the things that are the same size of each other. So a preorder is like a combination of a partial order and equivalence relation, if you have had enough maths classes to vaguely remember those things. Okay. Any other questions? Okay. So this sort of way of defining entanglement is actually just a specific example, and in some ways the sort of possibly the single nicest example of a very general thing that people do in quantum information, which is to define something called a resource theory. So this sort of theory of entanglement in terms of LOCC is an example of a resource theory. If you ever start sort of reading sort of quantum information papers, looking at the things that come out in the archive and stuff like that, you'll see that these things are all over the place. They're very, very common, particularly last few years. It's a very fashionable topic. And, you know, there's a good reason for that. It's a really beautiful and very, very, very general general framework that, yeah, lets you talk about all sorts of different topics within the same basic set of rules. Okay, so what are those rules? Well, the first thing that we define is we define some set of what's called free operations. Okay, so these are going to be sort of operations that you assume can be done very, very easily. Okay, and that you don't require any resource in order to do. Okay, so in this case, you know, within the particular resource theory describing entanglement, then the free operations are the local operations and classical communication. Okay, so we assume that those can be done easily. That Alice and Bob have excellent labs that you know, allow them to manipulate quantum states very, very precisely, and they also have good internet signal, good Wi-Fi signal, unlike me, and so can easily classically communicate. So then, with your set of free operations, there is some set of so-called free states that can be made, that can always be made using those free operations. Okay, so in this case, the free states that we can easily make are the separable states. Right, they're the things that are cheap if you can cheaply do these free operations. All other states are then defined as what's called resource states, that are useful resources that allow you to do things you otherwise wouldn't be able to do. So, for example, the useful resource of a Bell state, together with classical communication, that's something that would let you do quantum teleportation, for example, right? It's a useful thing that is valuable even if you're able to do these LACCs very, very efficiently and easily. Okay, so in this case, the resource states are going to be entangled states. And then we can compare different resources, so different entangled states, to one another by saying that some resource state A is necessarily more useful, or more precisely, at least as useful, as resource B, some other state. So entangled state A is at least as useful as entangled state B if you can make B from A using free operations. Okay, so we assume that these free operations don't cost us anything. We can do them all the time and no problem at all. So if that's the case, then you would always rather have or want to have resource A at least as much as resource B, because if it turns out you want resource B for any particular reason, you can always convert resource A into it without having to use anything you actually care about, right? Just using these free operations that you have unlimited amounts of. Okay, so that's sort of the theoretical framework that makes this LOCC be a nice definition of what it means to be entangled. It lets you say that assuming Alice and Bob have really, really good labs, they have good phone lines, but they don't have a good way to send quantum states between each other, then this notion of more entangled is the thing that lets state A be more useful to Alice and Bob than state B. Okay. Cool. Okay. Any questions about that? Awesome. Okay. So you might say, okay, but when we were thinking about pure states, we had this other definition of something being more entangled than something else, which was instead the entanglement entropy, right? So how does that sort of fit to this story? Is this sort of unrelated, completely different definition, or what? So it turns out you can show that if I have some state, pure state psi1, and I have another pure state psi2, then I can get from psi1 to psi2. If I can get from psi1 to psi2 using local operations and classical communication, then that implies that the entanglement entropy in psi1 has to be greater than or equal to the entanglement entropy in psi2. Okay, so this entanglement entropy is closely related to LOCC, in that there's an implication. The LOCC ordering implies the entanglement entropy ordering. On the other hand, in general, the other direction is not true. Okay, in particular, for any pair of states, we either have SA of psi1 is greater than or equal to SA of psi2, or we have the other way around, or we have both being true, right, if the two things are equal. Okay, whereas we do have states psi1 and psi2 where there's just no arrow going between them, no way to get between them using LOCC. So the sort of ordering from entanglement entropy extends the ordering from LOCC. And as much as sort of all if something is more entangled than something else according to LOCC, it also will be, but according to entanglement entropy, but entanglement entropy can compare more things. Okay. So this is an example of what's called an entanglement monotone. It just means that something that satisfies two things. One is that doing LOCC operations never increases it. And 2 is that it's 0 for all separable states. Okay, so that's enough to have the sort of ordering induced by this entanglement monotone extend the ordering you get from LOCC operations. Of course, this is very non-unique. In particular, you can have any function of the entanglement entropy would also satisfy these two properties, but there are also all sorts of other functions that will give different orderings give different answers for what is more entangled than what for the cases where LOCC is unable to compare them. Okay. In this case, it turns out that the entanglement entropy ordering is special. For the following reason, which is that let's say instead of wondering whether we can get just from psi1 to psi2 using LOCC operations, we ask whether we can get from n copies of psi1 to n copies of psi2. Turns out that in the limit of large N, with some appropriate definitions or approximations, then that is actually equivalent to the entanglement entropy of psi1 being greater than or equal to the entanglement entropy of psi2. Okay, so that's why entanglement entropy does have some sort of operational preferred definition, but it's only the sort of most natural best answer if you have these large number of copies of the same state. Okay. So this gives a very natural question. Which is that for mixed states, the von Neumann entrophies of the reduced density matrix on A and on B are no longer monotones, right? They're no longer 0. On separable states, they're no longer they no longer necessarily decrease when you do local operations and classical communication, right? You could just like do a measurement and then forget about the outcome of the measurement, and that will increase the entropy of one of your systems, even though it won't increase entanglement. It's just a local operation. However, nicely enough, turns out that there are other quantities that are still monotones for mixed states. Several of them actually agree with the entanglement entropy for pure states. So just to list off a load of them that you might have seen, heard of vaguely before. There's something called the entanglement of formation, which roughly, well, there's really two things. There's the entanglement of formation and there's the entanglement cost that are very closely related. And basically they quantify, if you're trying to make a large number of copies of the state rho AB, how many Bell pairs do you need to do it? Like what's the rate at which you need to use up Bell pairs in order to create those states, just using local operations and classical communication. There's another thing, which is the entanglement of distillation. And that's sort of the opposite. That's if instead of trying to create the state from Bell pairs, I'm trying to start with a load of copies of my state rho AB, and I'm trying to extract some Bell pairs out of it. How many Bell pairs can I extract using local operations and classical communication? There's something else called the relative entropy of entanglement. So this is just sort of an stupid or obvious definition, which is basically you take the minimum of the relative entropy relative to all separable states, right? So this is obviously 0 if it's separable and non-zero if it's not separable. But it turns out to be a monotone. It always decreases under LECC. There's also something you might have heard of called the logarithmic negativity, which I'm not going to go into, related to the state not having a positive partial transpose. But yeah, don't worry about that. And so, yeah, there's a lot of things that satisfy most properties, and many of them, particularly these three, for pure states, actually reduce to the entanglement. You might say, well, there's a million different meshes here. Surely there's one like preferred one, the best one. And the answer is that there honestly isn't really. Like for pure states, the entanglement entry is just the single nicest way to quantify entanglement. But in this case, these sort of things have different nice properties. Depending on what property you're looking for, then different measures are nicer. So for example, some are sort of nice and easy to calculate, so just practically easier to work with. Some are non-zero for all entangled states, right? So they're only 0 for separable states. They're all 0 for separable states, but some are 0 as well for entangled states. So that's a nice property you might want. That's something called a faithful entanglement monotone. Some have sort of nice operational interpretations, right? Like entanglement formation, entanglement distillation. They all sort of have different nice properties. And the sort of best one depends on what you care about. Okay. Okay, so any questions about entanglement monotones and why we should care about them, what the point of them is, stuff like that? Okay. Great. So I'm not going to go into any more detail into them because there's a lot to talk about, and you guys have projects to do. It's the very end of the semester, so I don't want to get too into the weeds of stuff. So instead, I'm going to move on to the sort of final thing I really want to talk about today, which is a very simple question of when can we get from one state to another using local operations, classical communication? Okay, like what are necessary sufficient conditions that would be possible? So for general mixed states, this is hard and messy and complicated. So I'm just going to do it. There's sort of the only case where you have a nice clean condition really is when the states are both pure. Okay, so you're trying to get from one entangled state psi 1 to some different pure entangled state psi 2 using local operations, classical communication. Okay, and in this case, we have a very nice and simple answer. Which is that you can do so if and only if the reduced density matrices rho 2a and rho 1a so the reduced density matrices of the states psi 1 and psi 2 satisfy the following property, which is denoted with this curly greater than or equal to symbol, which is that rho 2a majorizes rho 1a. actually this is equivalent. You might say why A rather than B. We could have written it in terms of row 2B and row 1B instead. That's completely equivalent definition. Okay. So what does it mean for one matrix to majorize another? Sort of two definitions of that which will be useful, which is maybe not totally obvious or equivalent, but are. The first is that it means that row 1 can be written as a classical mixture of row 2 conjugated by unitaries. Okay, so we take row 2, we conjugate it by a unitary, and then we take it weighted sum over different choices of what unitary to conjugate by. The second definition, which is sort of easier to check than whether this condition is true, is the following: that we write out row 1 and row 2 in their eigenbasis. So we say that row 1, sum over I, lambda 1i, psi 1i. Same for row 2. Then we need the following conditions to be true on the lambda. Yeah, and let's assume that we've written these eigenvalues lambda in sort of decreasing order. So the I equals 0, I equals 1 is the largest eigenvalue, I equals 2 is the second largest eigenvalue, and so on. So as I gets bigger, then lambda I gets smaller. Then we need the following condition to hold, which is equivalent to this condition that we had before, which is that for any j, then the sum over from I equals 1 to I equals j of lambda 2i has to be greater than equal to the sum over I up to j lambda 1i. Okay, so this means that we need to have the largest eigenvalue of row 2 be larger than the largest eigenvalue of row 1. We also need to have the sum of the two largest eigenvalues of row 2 be larger than the sum of the two largest eigenvalues of row 1, and so on all the way through. Okay, up to the sum of all but the last eigenvalue of row 2 being larger than the sum of all but the smallest eigenvalue of row 1. Okay, which since both sets of eigenvalues have to sum to 1, means that the smallest eigenvalue of row 1 needs to be bigger than the smallest eigenvalue of row 2. Okay, so this is just a natural condition of row 1 being like definitely more mixed than row 2. Okay, and this is very natural. We're wanting to say that as we use LOCCs, we always make the states less entangled, and that means that we make the reduced density matrices less mixed because the state's staying pure all the time. Okay, that makes sense to everyone? Any questions? Okay, so I'm just going to give, I actually have a bit more time than I thought, but I think I'll just let you guys go a bit early. So I'm just going to give a sort of very high level sketch of roughly how the proof works. So I'll leave you guys to prove, for example, that these two definitions are equivalent. That's not too hard. But yeah, I'll give a sort of sketch of the sort of things you want to argue to show that this is a necessary sufficient condition to get between psi 1 and psi 2 using LOCC. Okay. So the first thing to note is that applying local unitaries to A and B leaves these eigenvalues unchanged. Right, so yeah, if we apply a local unitary to say A, then it changes the eigenstates in the reduced density matrix of A, but it doesn't change the eigenvalues because the reduced density matrix of B is unchanged and A and B have the same eigenvalues. And just, yeah, conjugating a matrix with a unitary doesn't change the eigenvalues. But this is the sort of only constraint on what you can do with local unitaries. We can use local unitaries to go between any pair of states with the same set of eigenvalues lambda I. Okay, so yeah, if we can get the lambda i's right, then local unitaries will deal with the rest. Okay, so the hard part is going to be, how do we change these lambda i's to get them to be what we want? And of course, the answer is we only have one thing we can do to the state other than just apply local unitaries, which is to do measurements. Or rather, sort of generalized measurements. So the most general definition of a measurement we saw in the course is some set of Krauss operators, Ki, which of course have to add up to the identity. And then when you do the measurement, then psi gets updated to Ki psi divided by square root Pi with probability Pi equal to the expectation of Ki dagger Ki in state psi. Okay, that was this is the positive operator in the POVM. This is the update rule for the particular Krauss operator Ki. This is what we saw a load of lectures ago before quantum error correction and all that stuff. And it's pretty easy to see that because these Ki's are non-unitary, then they can change the lambda i's even when, say, Ki only acts on A, right? Like Alice has just done a local measurement in her lab. Okay, so what we want to try to understand is, what we can do with these Ki's, how we can change them. And the first thing to note is that if we don't condition on sort of Alice's measurement outcome, right? So Bob, say, doesn't know Alice's measurement outcome. Then from Bob's point of view, his reduced density matrix is unchanged by this process because he hasn't done anything at all in his lab. But of course, if we do condition Alice's measurement outcome, then his state is no longer the reduced density matrix of psi. It's the reduced density matrix of Ki acting on psi divided by square root of Pi with probability Pi. Okay, so we must have this reduced density matrix rho B is equal to the sum over I of Pi times rho IB, where this is the reduced density matrix of Ki psi divided by square root Pi. Okay. So Bob once Bob learns Alice's measurement outcome, he'll discover the state is actually in state row I, but his expected state on learning that has to be the same as what he thought the state was in advance. And so we need this condition that yeah, the original reduced density matrix is just a classical mixture of the final ones. Okay. So let's say we're just going to have Alice do one measurement, and then we're going to do sort of local unitaries and stuff, and we're going to hope to eventually produce the state psi2, which we're trying to get to. Okay. Then we would need to have the row i's of Bob's reduced density matrix be equal to the target reduced density matrix conjugated by some local unitary, right? So you know, the local unitary can be different depending on which measurement outcome we got, because Bob can do different things once he learns Alice's measurement outcome, depending on what that outcome is. But if he's only going to do local unitaries after that, then you know, the final state he's going to end up with has to be row 2, and so the state row I has to be related to row 2 by conjugation by some unitary. Okay. So this is, so Bob can get his reduced density matrix to row 2 using just local unitaries. Okay, but then this condition that we had here, combined with this condition that we want to be able to make row 2 just using local unitaries after we've done that measurement, automatically implies that row 1 is equal to a sum of I, pi, ui row 2, ui dagger. But that, already said by definition, is equivalent to row 2 majorizing row 1. Okay, so that's sort of what we wanted to show. Yeah, this is not a complete proof. There's various additional things you need to show to get to the point of arguing that majorization is a necessary and sufficient condition for getting between pure states using LACC. The first is that this is also a sufficient condition to get from row 1 to UI row 2 UI dagger using a single measurement. So this turns out to indeed be true. One way to sort of see roughly why it's true is that the only constraint on these KIs is that they have to add up to the identity, and that constraint is basically what gave us this constraint, that the you know, the original row B has to be an average sum over the row I's. But it's also, you can just explicitly construct KIs that do what you want them to do, that give the row 2s as desired. The second thing, so this can be constructed explicitly pretty simply. It's not terribly insightful, so I won't go through it. The second thing you might worry about is that we assumed there was just a single measurement done by Alice and then local unitaries done by both of them, right? So the second thing you want to show is that using multiple measurements, you know, maybe Alice does a measurement, and then depending on what outcome she got, Bob does a measurement in some different basis. Okay, sorry about that. I don't know what happened. Wi-Fi is being weird today. Let me, okay, I'm back. Okay, cool. Whoops. So yeah, the second thing we wanted to show is that using multiple measurements can't help. And basically the way you argue that that's true is that after each measurement, then sort of the new reduced density matrix, depending on the outcome of that measurement, on average, that new reduced density matrix majorizes the old one. Okay, you can define that precisely, but the point is that each step you like sometimes you might get lucky and get something that doesn't majorize the old, get something more entangled if you have some basis that includes a more entangled state. Yeah, but in general, on average, it's going to make it less entangled at each step. It's going to majorize it at each step, and so you can't end up with something that doesn't majorize your initial thing and have that with 100% certainty. Okay, so I'll leave you guys to look into that if you're interested. I'm just going to end with sort of very simple thing, just because we ended up quite abstract and in the weeds there. Just sort of an example of like, how this gives you this sort of pre-ordering and like you can only go between certain states and so on. And so the example is going to involve Q-trits. It's the sort of smallest case, which is interesting. And we're going to consider 4 different states. Okay, so we're going to have one state here that is just going to be maximally entangled between the 2 Q-trits. Going to have another state that's just going to be some product state. Okay, it doesn't have to be necessarily a product state in the sort of computational basis. It could be something like 0, 0 plus 1, 0, but it's still just a product of 0 plus 1 with 0. Going to have another state, which is going to be, again, an entangled state, but not maximally entangled. So I just made it this plus something like this, say. And final state, which I'll put over here, going to make be another kind of entangled, but not completely entangled state. Okay, so these are just some simple examples. There's obviously infinitely many states, but yeah, let's look at these. Okay, so this maximally entangled one, we can look at the reduced density matrix. It's maximally mixed because the state was maximally entangled. So it's eigenvalues 1/3, 1/3, 1/3. Similarly, this bottom one is a pure state. So its eigenvalues are just 1, 0, 0. So reduced density matrix. This one, we have a half, a quarter, a quarter. And finally, this one, we have 2/5, 2/5, 1/5. Okay, so we want to see which ones we can go between using LOCC. And so the first thing to note is that if we start with this maximally entangled state, we can get to anything. So it's very easy to check. So a third is smaller than any of the largest eigenvalues of any of them. A third plus a third, which is 2/3, is also smaller than the sum of the 2 largest eigenvalues of any of them. So we can always get from maximally entangled state to anything we like using LOCC. And that's generally true. Maximally entangled states are more entangled than any other state. Okay, with also the case that this product state has eigenvalues 1, 0, and 0. So that majorizes anything, right? Because the largest eigenvalue is already 1. The sum of the k largest eigenvalue is also 1. And so for any other state, it will always be less than or equal to 1. And so we can get from here to here as well. But we also have these two states, right? So on the left, we have the state with eigenvalues a half, a quarter, a quarter. Right, we have 2/5, 2/5, 1/5. So let's try and see if we can get from one of them to the other. Well, a half is bigger than 2/5. That means we definitely can't get from the left state to the right state, because that would make the largest eigenvalue smaller. It doesn't majorize it. But we also have that a half plus a quarter is 3/4, which is less than 2/5 times plus 2/5, which is 4/5. And so we also can't get from the right state to the left state using LOCC, because that would decrease the size of the sum of the two largest eigenvalues. So this state and this state are just differently entangled. Okay, so that's pretty much all I want to cover today. Just make some brief final comments. The first is, yeah, as I said before, there's no such nice, necessary, and sufficient condition for mixed states. Really is, LOCC, LOCS. This really is special to pure bipartite states. Just nice enough to have this work. You don't even have like a nice Schmidt decomposition for mixed states or anything like that. This LOCC definition of entanglement very easily generalizes to the case where you don't just have Alice and Bob, you have more labs, you have 3 or 4 or 5 labs. This is called multipartite entanglement. But of course, as with even just going to mixed states rather than pure states, it very quickly becomes very like non-clean. There's at least no known nice characterizations of entanglement structure, and like when something is more entangled by another thing. So it gets very messy very fast the moment you go beyond bipartite pure states, to be honest. Okay, that's really all I have to say. Ooh, we have one thing in the chat. Yeah, that's a good question of whether there's a question in the chat about whether this is covered in Riefel and Pollock. I should have checked that in advance. I think it maybe talks about it a bit, but not in much detail. Nielsen and Truong will definitely go through this in detail. In fact, Michael Nielsen came up with a lot of this stuff, so I'm sure Nielsen and Truong covers it well. It's also just Google like LOCC entanglement, and you'll find reviews of this sort of thing. There's a good Michael Nielsen review actually that goes through all the proofs in detail, which is entanglement bipartite states or something. Majorization bipartite states. Nielsen should find it for you. That's all I have to teach you guys this semester. Thanks for everyone showing up all the way through, or for watching on YouTube all the way through if you're doing that. It was fun to teach you guys. Sorry it was over Zoom. Next week, obviously, we'll have the presentations, which will be fun. So this isn't the last you'll see of me. Any questions though on the last part of today?
What are you going to eat for Thanksgiving?
Steak. I have some steak. I have some cranberry relish. Yeah, some stuff like that. Never had steak with cranberry relish, but there was some cranberry relish around, and I thought I should get a bit Thanksgiving-ish. Yeah, I don't understand. Okay, someone explain this to me. You guys can teach me. Possibly we should stop recording, but whatever. This can just be at the end of the YouTube video. Why in America do you have Thanksgiving and then like less than a month later Christmas, and the standard thing, as far as I can tell, for both is like turkey? Like who wants to have 2 giant turkeys like a few weeks apart? That's just excessive turkey.
I don't know if turkey is the standard thing for Christmas, but I'm also
Okay.
a Jew, so I can't really say.
Yeah, it seems like it's less standard for Christmas because everyone's bored of it after Thanksgiving. But I've never got people to tell me. I mean, maybe there just isn't a standard thing for Christmas in this country, because I've never had anyone explain to me like what the non-turkey thing that's standard for Christmas is.
I think a lot of people, or at least oftentimes I've seen my family or people do glazed ham for Christmas.
That's
True.
That's solid. I'm fine with that at Christmas. I normally do. My family used to do that for Christmas Eve and then do turkey for Christmas. Yeah,
Let's see.
works well.
But when you were in England, you didn't celebrate Thanksgiving, right?
Yeah, exactly. So then that's what I'm saying.
Then
So
there's a
to
standard
me,
amount of
people
turkey.
the standard thing is turkey for Christmas, but then here you have turkey for Thanksgiving. So it's like, oh, what's Christmas then? And
I don't think
that's
there's
just not a standard thing.
Yeah, I don't think so. But again, I don't celebrate Christmas, so I only know this.
Yeah. Whatever. Anyway, yeah, thanks everyone. If there's no actual physics questions, then I will stop the recording. Last chance to ask something. Okay.